Hello everybody, welcome into another lesson. So today we are going to talk about taking roots and powers of complex numbers. And we're actually going to start out raising them to powers. So you have something here called DeMoivre's theorem. Forgive me for not pronouncing it the best. French was probably the Romance language I was not the greatest at. I've studied Spanish, I've studied German, which I know is not a Romance language. I've studied even a little bit of Portuguese, and I took Latin in high school, but French I was never the best at. But DeMoivre's theorem says that if you want to raise a complex number to a power, it's going to be the same as that r to that power times the quantity of the cosine times the number of the power times theta plus I times the sine of that number of the power times theta. Now, let's say you had something like 2 plus 3i to the 20th power. You could, of course, use the binomial theorem to expand this and get your result. And if you want to do that, by all means, knock yourself out. But DeMoivre's theorem is so much simpler to work with instead of using the binomial theorem, because this would be awful to try to use the binomial theorem for. So let's go ahead and get started with some examples, and I'll leave this up while we work on these. So let's just start out with, let's say we had something like 1 plus I to the third power. Of course, using the binomial theorem for this wouldn't be too bad, but we're not going to do that today. So, according to DeMoivre's theorem, we need to find first that r. So, the r for this, of course, is going to end up being the square root of my a squared, which is 1 squared, plus my b squared, which is also 1 squared. So that would end up being the square root of 1 plus 1, which would be the square root of 2. So my r is the square root of 2. Now we need to find theta. So we'll take the tangent of theta will equal b over a, which is 1 over 1, or simply 1. And you notice both your A and B are positive, so this will be a first quadrant angle. So that means theta is going to end up being 45 degrees. Alright, so we've identified R, we've identified theta. We're ready to use this formula. So we can say that 1 plus I to the third equals that R, which would be the square root of 2 raised to the third power times the quantity of the cosine of, alright, so the number, that n is the power I'm raising this to, so that would be 3 times 45 degrees plus I times the sine of 3 times 45 degrees. Well, the square root of 2 to the third power, that's going to be 2 times the square root of 2. And then we'll have the cosine of, alright, so 3 times 45, that's 135 degrees. So this will be the cosine of 135 degrees plus I times the sine of 135 degrees. So we're almost done. This is the trigonometric form. We want to get it as a result in standard form. So let's go ahead and find these values. 2 times the square root of 2 times, okay, 135 degrees we know is a 45 degree angle in the second quadrant. So the cosine of 45, but in the second quadrant, that's going to be negative 1 over the square root of 2 plus, that would be I times the sine of 135, that's positive 1 over the square root of 2 which would then just equal -2 plus 2i. So I was able to use DeMoivre's theorem to expand 1 plus I to the third power and get -2 plus 2i. Sometimes, especially if you get into higher powers, this is much easier to work with than using the binomial theorem. Alright, I got plenty more where that came from. I think the next one's going to be the 6th power, so that's even going to be greater. Alright, so we're going to take 2 plus 2i, raise that to the 6th power. Again, this is one you probably would not want to use the binomial theorem for. So let's go ahead and find our r. Let me correct my dog real quick. Weenie, come on, bud. I'm trying to teach. Come here. Come here. Come down, buddy. Come on. Sorry, folks, my dog. My dog likes to bark a lot. He likes to go to the window and bark. I have a miniature dachshund, so... Yep, anyway. We have 2 plus 2i to the 6th power. If we want to find r, we'll take the square root of our a squared plus b squared, so that would be 2 squared plus 2 squared. Well, that's going to equal the square root of 4 plus 4, or simply the square root of 8, which would end up being 2 times the square root of 2. Alright, so there's our r. Let's find theta. So the tangent of theta would equal b over a, which is 2 over 2, or simply 1. Well, some good news here is that this is in the first quadrant because a and b are positive, so theta is going to be 45 degrees again. This is so much easier to work with. Okay, we got r, we got theta, we can proceed now to finding this complex number to the 6th power. So 2 plus 2i raised to the 6th power is going to be my r of 2 times the square root of 2 raised to the 6th power times the quantity of the cosine. Now my n is my power, so that's going to be 6 times 45 degrees plus I times the sine of 6 times 45 degrees. Okay, so let's take 2 times the square root of 2 to the 6th power. Well, we know 2 to the 6th power is going to end up being 64 times, what is the square root of 2 to the 6th power? That's going to be 8. So we have 64 times 8 times the cosine of 6 times 45. That turns into the cosine of 270 degrees plus I times the sine of 270 degrees. Now, what the heck is 64 times 8? I know it's going to be a big number. That's going to be 512. So that's going to equal then 512 times, all right, the cosine of 270, that's 0, plus I times the sine of 270, so that'd be plus I times -1, which would simplify into negative 512i. So 2 plus 2i raised to the 6th power is going to be negative 512i. Much better than trying to use the binomial theorem. Alright, so we have negative 1 plus I raised to the 10th power. So we got negative 1 plus I raised to the 10th power. Okay. Well, let's go ahead then and find R. So R is going to equal that square root of that negative 1 squared plus the 1 squared. So that would be the square root of 1 plus 1, or simply the square root of 2. So R equals the square root of 2. Now let's find theta. So the tangent of theta is going to equal 1 over negative 1, or simply negative 1. Okay. Well, your A is negative, your B is positive, so this is actually going to be a second quadrant angle. So the tangent of theta being negative 1 in the second quadrant, that would be 135 degrees. So theta is going to equal 135 degrees. Alright, now we are ready, since we have R and theta, we're ready to proceed to find the complex number expanded to the power. So negative 1 plus I to the 10th power would equal my R, which is the square root of 2 raised to the 10th power, times the quantity of the cosine of my power, which is 10 times my theta, 135 degrees, plus I times the sine of 10 times 135 degrees. Alright, so square root of 2 to the 10th, that's going to be 32 times, let's see, 10 times 135, that'd be the cosine of 1,350 degrees, plus I times the sine of 1,350 degrees. Well, we're well over 360, aren't we? We can definitely simplify this. Let's figure out the equivalent of 1,350 from, this is several rotations around the circle. Let's figure out from its first rotation. You actually end up getting 270. So this would turn into the cosine of 270 degrees plus I times the sine of 270 degrees. So this is going to equal 32 times cosine of 270 is 0. Sine of 270 is negative 1, so this would be minus I. So you should simply get negative 32I. So your final answer should simply end up being negative 32I. And I got one more I want to do. It's going to be kind of similar, but we're going to really take it up a notch. We're going to take 1 plus I, we're going to raise it to the 100th power. Definitely not wanting to use the binomial theorem for this, are we? I wouldn't think so. So let's go ahead, let's find our R. So that's still the square root of a squared plus b squared. So the square root of 1 squared plus 1 squared. That's going to then equal the square root of 1 plus 1, which is the square root of 2. Alright, so R is the square root of 2. Let's find theta. So the tangent of theta equals b over a, so 1 over 1, or just 1. Well, both A and B are positive, so that'll be in the first quadrant. So theta is going to equal 45 degrees. We know r, we know theta. Let's go ahead now and find the complex number to the 100th power. So 1 plus I raised to the 100th power is going to equal my r, which is the square root of 2 raised to the 100th power, times the cosine of my power times the angle, so 100 times 45 degrees plus I times the sine of 100 times 45 degrees. Okay, so the square root of 2 to the 100th is the same as 2 to the 50th power. Let's figure out what the heck that's going to look like. It's not pretty. Let's see, millions, billions, trillions, quadrillions. Wow. This is awful. You get 1 quadrillion, 125 trillion, 899 billion, 906 million, 842,624, all that times the cosine of 4,500 degrees, plus I times the sine of 4,500 degrees. So let's write this out then. So this is going to be that 1 quadrillion, 125 trillion, 899 billion, 906 million, 842,624 times, alright, let's figure out what 4,500 is in terms of 0 to 360. Because we're well over the 360. You get 180. So this would be the same as the cosine of 180 degrees plus I times the sine of 180 degrees. That's a form we can work with so much better. Alright, so this is going to end up equaling that 1 quadrillion, 125 trillion, 899 billion, 906 million, 842,624 times, what's the cosine of 180? That's negative 1 plus I times the sine of 180. That's just 0. So your final answer should be negative 1 quadrillion, 125 billion, 125 trillion. So negative 1 quadrillion, 125 trillion, 899 billion, 906 million, 842,624. This is a fine example of why you probably wouldn't want to use the binomial theorem for this, because of answers like what you get here. This shows you the extremeness of what you can do without having to use the binomial theorem. So that was a fun one. Alright, so we've raised the powers. Now we're going to do the inverse of that. We're going to take roots of complex numbers, which is derived from DeMoivre's theorem, because after all, a root is a power. It's just a reciprocal power. So let's say I want to take some nth root of a complex number. So this time we're taking the root of a complex number. Well, that's going to be equal to that root of my r times the cosine of my theta plus 2 pi k all over n plus I times the sine of my theta plus 2 pi k over n. Alright, so you're probably wondering, well, what the heck is the k? You probably get the n, that's your number of the root, but what is k? So, let's say let's say, for example, this was the sixth root. I was taking the sixth root of z, of my complex number. K tells you, well, the n tells you how many solutions you should have. If I have a sixth root of a complex number, I'm going to have 6 solutions. So k equals n minus 1. That means I should have, for k, I should have 0, 1, 2, 3, 4, and 5. I'm going to have 6 solutions for the sixth root of a complex number where k is 0, 1, 2, 3, 4, and 5. So let's get started with some examples here. This is definitely one you couldn't use the binomial theorem, but let's say I start out with something simple like the square root of 2i. So this enables you to take the square root of complex numbers, where before we couldn't do that. So the square root of 2i, well, we know that's a second root, right? Well, let's find r. What is r? R is going to be, we only have a b term, so the square root of 2 squared is just 2. Okay, r is 2, that's easy. Now what about theta? The tangent of theta, that's going to be b over a, which is going to be 2 over 0. We know that's undefined. We do know that. But what gives us an undefined tangent where you have a positive in the numerator? That'd be 90 degrees, right? So theta itself is 90 degrees. So now we know r, we know theta. So if you want to take the square root of 2i, you're going to have then 2 answers. You'll have 2 answers. So for k equals 0, so we're going to do it for k equals 0. The next root should be when k equals 1. So we're going to take the second root of 2, so we'll have the square root of 2, the square root of that r, times the cosine of 90 degrees plus 2 pi times 0. Well, that's just 90 degrees. So that would be 90 degrees divided by my n, which is my root number. So that would be 2 plus I times the sine of 90 degrees plus 2 pi times 0. That would just be 90 degrees all over 2, which is going to equal the square root of 2 times the cosine of 45 degrees plus I times the sine of 45 degrees. Alright, well, these are both first quadrant angles, so this would equal the square root of 2 times 1 over the square root of 2 plus I times the sine, or I times 1 over the square root of 2 which should simply give you 1 plus I. So one of the square roots of 2i is going to be 1 plus I. Now we need to evaluate this for when k equals 1. The highest number of k you go up to is where k equals n minus 1. So that if you have a second root, that's going to be 2 minus 1. You go up to when k equals 1. Okay, so that's one of your square roots. Let's find the second square root. So you're still going to have the square root of r, so that would be the square root of 2 times the cosine. Now 90 degrees plus 2 pi, that's going to be 450 degrees divided by 2 plus I times the sine of 450 degrees divided by 2. Well, that's going to simplify then into the square root of 2 times the cosine of 225 degrees plus I times the sine of 225 degrees. So 225 is in the third quadrant. So this is going to be the square root of 2 times negative 1 over the square root of 2 plus I times negative 1 over the square root of 2, which when you do the multiplication, you should end up getting negative 1 minus I. So now we have just found both square roots of 2i. You get 1 plus I and negative 1 minus I. So that's how we start out finding roots. Okay. Let's do another with square roots, and then we'll even do some higher powers. Let's do the square root of 2 plus 2i. Since this is going to be a second root, that means we should have two solutions. So we're going to evaluate the square root of 2 plus 2i. So let's find our r. That's going to equal the square root of 2 squared plus 2 squared, which would be 4 plus 4, or 8. So you would end up getting 2 times the square root of 2 for your r. The tangent of theta, alright, so that's going to be 2 over 2, which would simply be 1. Since we're in the first quadrant, theta is going to be 45 degrees. So we have a theta of 45 and an r of 2 times the square root of 2. Well, now we need to find both roots. So let's do this when k equals 0. All right, so k equals 0. So that's going to be, of course, the square root of my r, which is the square root of 2 times the square root of 2. Yeah, that looks pretty messy, doesn't it? Times the cosine of my 45 degrees plus 2 pi k. When k is 0, you'll just get 45 degrees divided by 2 plus I times the sine of 45 degrees divided by 2. So this is going to equal the square root of 2 times the square root of 2 times the cosine of 22.5 degrees plus I times the sine of 22.5 degrees. Well, we're definitely going to end up getting some decimal approximations. This is not going to be fun. But that's the best we can do. So let's see what we get. Sometimes you will have that. All right, so you get approximately 1.55 plus, now let's take this result and do it times the sine of 22.5. 0.64i. So your first root is approximately 1.55 plus 0.64i. The first of the square roots, you still have a second square root you have to consider, which is when k equals 1. So again, this time we're going to take the square root of that r, which is the square root of 2 times the square root of 2, times the cosine. All right, so theta was 45 degrees plus 2 pi times 1, so that's going to be 405 degrees divided by 2 plus I times the sine of 405 degrees divided by 2, which is going to end up equaling the square root of 2 times the square root of 2. Now let's figure out what the heck 405, that should be 202.5. That'd be times the cosine of 202.5 degrees plus I times the sine of 202.5 degrees. So this is going to get a little bit messy again. Definitely in the third quadrant this time. You get about negative 1.55 for your real component, and then let's take that times the sine of 202.5. Negative 0.64. So your second root should be approximately negative 1.55 minus 0.64i. These are both of your square roots for 2 plus 2i. All right, so let's do a cube root one. I'll keep them relatively simple. We're going to do a cube root, then we're even going to do a fourth root, and then we'll call it done for the day. Alright, so I want to find the cube root of negative 27i. So this time we're doing the cube root. Let's establish that my n is 3, which means for k I need to have, those are all n minus 1, so I need to have 0, 1, and 2. That means I'm going to have 3 cube roots with those values of k. Alright, so let's find r. Well, r, if we take that negative 27 squared and take the square root of that, you just get 27. R is going to equal 27. That one's pretty easy. Now, what about theta? You have this is really 0 minus 27i. So we could say the tangent of theta equals negative 27 over 0, which we know is undefined, but what angle gives you a tangent where your numerator is a negative and your denominator 0? That's going to be 270 degrees, right? So that means theta is going to end up equaling 270 degrees. Alright, so we know r, we know theta. Let's start out when k equals 0. We're going to have 3 roots because we're taking the third root of this. So first this will be, since this is the third root, so you'll take the third root of your r, which is 27, times the cosine of your theta, which we determined was 270 degrees, plus 2 pi times 0. Well, that would just be 270 degrees divided by my n, which that's my root, so 270 divided by 3 plus I times the sine of 270 degrees divided by 3. Okay, so what's the cube root of 27? That's just 3, right? So we'll end up getting 3. Now 270 divided by 3, that'd be 3 times the cosine of 90 degrees plus I times the sine of 90 degrees, which makes this not so bad, because what's the cosine of 90? That's just 0. Sine of 90 is 1, so you just end up getting 3i for your first of the 3 roots. So your first answer, when k equals 0, you should get positive 3i. Now, let's do this when k equals 1. So we're going to again take the cube root of r, which is 27. Well, we already know that's 3. This time times the cosine. So our angle was 270 degrees plus another 2 pi. So we need to, if k is 1, we're going to add 360 to 270. That would be 630 degrees divided by 3 plus I times the sine of 630 degrees divided by 3, which would end up equaling 3 times the cosine of 210 degrees plus I times the sine of 210 degrees. Well, this root is not so nice, is it? This third root will not be so nice. 210 degrees is a 30-degree reference angle in the third quadrant, right? So this is going to be 3 times... What's the cosine of a 30-degree angle in the third quadrant? That'd be negative square root of 3 over 2. And then the sine of 210, that would be negative 1/2, so that'd be minus 1/2 I. So your final answer should be negative 3 times the square root of 3 over 2 minus 3/2 I. That's for when your k equals 1, so that's the second of the 3 roots. So far you have positive 3i and then negative 3 times the square root of 3 over 2 minus 3/2 I. There's still one more root to consider. That's when k equals 2. We still have to consider when k equals 2. So take the nth root of r, the third root of your r, which is the third root of 27, that's going to be just 3 times the cosine of, okay, we had 270 degrees. This time the k is 2, so 2 times 360 is 720. So we need to add 270 plus 720, you get 990. That would be the cosine of 990 degrees divided by 3 plus I times the sine of 990 degrees divided by 3, which would simplify into 3 times the cosine of 330 degrees plus I times the sine of 330 degrees. Now this is going to be a 30-degree reference angle in the fourth quadrant, so this won't be so bad. So this would be 3 times, what's the cosine of 330? That's going to be positive square root of 3 over 2. And then the sine is negative in the fourth quadrant, so that'd be minus 1/2. So for your last third root, you should get positive 3 times the square root of 3 over 2 minus 3/2 I. Alright, so your 3 third roots are going to be positive 3i, negative 3 times the square root of 3 over 2 minus 3/2 I, and then positive 3 times the square root of 3 over 2 minus 3/2 I. Those are all 3 of your third roots for negative 27i. And you guessed it, yes, we're actually going to do a fourth root, and then we'll be done with the lesson. I'm going to take it real easy since we're doing a fourth root. Let's just take the fourth root of I. So we're going to take the fourth root of I. So that means my n is 4. So that means all my k values, I need to have 4 roots. So that's going to be when k equals 0, 1, 2, and 3. Those are the 3 values of k I need to use. Okay, let's find r. Well, the square root of 1 squared is just going to be 1. So my r equals 1, which is pretty nice. Now, what about my theta? Okay, so the tangent of theta is going to equal 1 over 0. Well, that's going to, the theta will be 90 degrees because I get a positive numerator with an undefined value at 90 degrees when I take the tangent of 90. Alright, so we know r, we know theta. Let's go ahead now and start finding the roots. So let's deal with when k equals 0. When k equals 0, well, the fourth root of my r, the fourth root of 1, I would take that as just going to be 1. I don't even need to write that. We can skip that part. This is just going to be the cosine of my theta, which is 90 degrees, plus 2 pi k. Well, k is 0, so it'll be 90 degrees divided by 4 plus I times the sine of 90 degrees divided by 4. Well, 90 divided by 4 is 22.5, so that would equal the cosine of 22.5 degrees plus I times the sine of 22.5 degrees. Well, this is definitely going to be a decimal approximation. So let's go ahead and evaluate this. Cosine of 22.5 is about 0.92. Plus, let's deal with the sine of 22.5. That's about 0.38i. So the first of the fourth roots would be approximately 0.92 plus 0.38i. Well, we still have to deal with when k equals 1, 2, and 3. Let's go with when k equals 1. Well, it's still going to be the fourth root of our r, which is 1, so we don't even need to write that, but it's going to be the cosine of, alright, so 90 degrees plus the k is 1, so 90 plus 360, that's going to be 450 degrees divided by 4 plus I times the sine of 450 degrees divided by 4. So let's see what that gives us. 450 divided by 4 is probably not going to be a nice number. 112.5. So that would equal the cosine of 112.5 degrees plus I times the sine of 112.5 degrees. This will be yet another decimal approximation. So let's go ahead and find that. You get about negative 0.38 plus, let's see what the sine of 112.5 is. 0.92i. So your next fourth root is going to be negative 0.38 plus 0.92i. Alright, so we've dealt with when k equals 0 and k equals 1. Now we need to deal with when k equals 2. Alright, so still the fourth root of that 1, which is just 1. This will this time be the cosine of, alright, so theta was 90, so k is 2, so that's going to be plus 720. So that should end up being 720 plus 90, that's going to be 810 divided by 4. Plus I times the sine of 810 degrees divided by 4. Well, let's figure out what 810 divided by 4 is. 202.5. So this would end up being the cosine of 202.5 degrees plus I times the sine of 202.5 degrees. And we should get yet another decimal approximation. Get negative 0.92. Then let's take the sine of 202.5, negative 0.38i. So your third of the fourth roots should be negative 0.92 minus 0.38i. And then we have one more. We got to consider when k equals 3. So as you can see, taking roots can get very hairy very quickly. So again, the fourth root of that 1 is just 1. We don't even need to write that. So we're going to take, when k equals 3, that's going to be 360 times 3, which should be 1080, plus 90. That should be 1170 if I'm not mistaken. So yep, it's 1170. So this would end up being the cosine of 1170 degrees divided by 4 plus I times the sine of 1170 degrees divided by 4. Which should end up being the cosine of 292.5 degrees plus I times the sine of 292.5 degrees, which will result in another decimal approximation. So you get positive 0.38 for your real components. And then there's no doubt that we're going to have a negative I value. Minus 0.92i. Alright, so we now have all 4 of the fourth roots of I. You get about 0.92 plus 0.38i when k equals 0. Negative 0.38 plus 0.92i when k equals 1, negative 0.92 minus 0.38i when k equals 2, and 0.38 minus 0.92i when k equals 3. So that's it for doing roots and powers of complex numbers, and that's actually it for a while for trigonometry. The next lesson we're going to get into the unit of solving systems of equations and doing matrices, and actually one new topic will be introduced called partial fraction decomposition. But the next lesson is going to be solving systems of 2 equations with 2 variables. So I hope everyone has a great day. Take care.